What if you could hear the very first sounds of the universe? Not the crash of ocean waves or the rumble of thunder, but something far older, more profound. A whisper so ancient it carries the memory of creation itself, echoing across nearly 14 billion years of cosmic history. These are the primordial vibrations left behind by the Big Bang, ripples in the fabric of space and time that scientists are now learning to decode. Think of it as a cosmic recording etched into the heavens, waiting for us to press play. This isn't just a story about distant stars or abstract physics. It's a detective story, one where the clues are written in light, sound, and gravity. Picture researchers hunched over telescopes and supercomputers, sifting through static and shadows, searching for patterns that reveal how everything began. The tools of their trade, gravitational waves that bend spacetime itself, and cosmic microwave background radiation, the faint afterglow of the universe's explosive birth. These echoes are like fingerprints, each one telling us something new about where we came from and how the cosmos took shape. But here's what's truly astonishing. This isn't just about the past. By listening to these echoes, we're uncovering secrets that could redefine our future. What if the universe's first moments hold the key to understanding dark energy, the fate of galaxies, or even the possibility of other dimensions? The more we learn, the more we realize how much we've yet to discover. So join me on a journey to the edge of time, where the universe's oldest sounds are still ringing, and where every new revelation brings us closer to answering the biggest question of all: how did everything begin? The Big Bang wasn't just a moment, it was the first symphony ever played. Imagine the entire universe compressed into a space smaller than a single atom, hotter than the core of a star, vibrating with unimaginable energy. In that instant, space itself stretched faster than light, carrying those primal vibrations outward like echoes in an endless hall. But here's what's fascinating: these weren't sound waves as we know them. Without air to carry vibrations, the early universe created its own kind of music, ripples in the very fabric of space-time, pulsing outward as space expanded. Scientists call these quantum fluctuations, tiny variations in density that would eventually shape the cosmos we see today. Picture a vast cosmic drumhead being struck. The resulting vibrations didn't fade away. Instead, they froze into the structure of the universe as it cooled, becoming the seeds for galaxy clusters and cosmic voids. This explains why we find galaxies strung across space like beads on a necklace, following patterns set in motion during those first chaotic moments. What's truly remarkable is how we're able to study these ancient vibrations today. Just as archaeologists piece together history from pottery shards, cosmologists reconstruct the universe's birth using two extraordinary tools: the cosmic microwave background, a snapshot of the infant universe's glow, and gravitational waves, the space-time ripples predicted by Einstein. These are our time machines, letting us peer back to when the cosmos was less than a trillionth of a second old. Every irregularity in the cosmic microwave background, every faint gravitational wave signal, is like finding another page of the universe's hidden diary. This research is rewriting textbooks right now. Recent discoveries suggest these primordial sound waves might reveal secrets about dark matter's nature, or why the universe expanded so rapidly during inflation. Some theories even propose these vibrations could be evidence of other universes' cosmic neighbors brushing against our own in those first unimaginable moments. The deeper we listen, the more we realize the Big Bang wasn't an ending. It was the first note in an ongoing cosmic melody that continues to shape everything around us. That faint glow you see in static between television channels, that's not just random noise. It's the cosmic microwave background, the oldest photograph ever taken. Captured when the universe was just 380,000 years old, this afterglow shows us the moment light broke free from the primordial soup of particles. Before this instant, the cosmos was so dense that photons couldn't travel far without colliding with charged particles, making the universe opaque like thick fog. But as space expanded and cooled, electrons and protons finally combined to form neutral atoms, clearing the cosmic mist and allowing light to stream across the universe for the first time. What makes this glow so special are the tiny temperature variations, slight differences of just 1 part in 100,000. These aren't random imperfections. They're cosmic hieroglyphs encoding how matter was distributed in the infant universe. Warmer spots show where matter was slightly denser, colder spots where it was more sparse. Over billions of years, gravity amplified these subtle differences, pulling matter into the structures we recognize today, galaxies clustered along invisible cosmic filaments, separated by vast empty voids. It's as if we're looking at the blueprint for everything that exists. Modern telescopes like Planck and WMAP have mapped these variations with stunning precision, revealing patterns that look remarkably like sound waves frozen in time. Just as a musical note's pitch depends on the size of the instrument that created it, the spacing of these hot and cold spots tells us about the universe's early conditions. The dominant pattern, peaks separated by about 1 degree in the sky, corresponds to acoustic oscillations from when the universe was a seething plasma. This cosmic bass note gives us the universe's vital statistics, its age, composition, and even how fast it's expanding. But the CMB isn't just a relic, it's an active tool for discovery. The way light from this background gets distorted as it passes through galaxy clusters helps us map dark matter's invisible scaffolding. Subtle twists in the light's polarization may carry whispers from the universe's first trillionth of a second, potentially revealing evidence of cosmic inflation. Some researchers even hunt for anomalies, unexpected cold spots, or strange alignments that could hint at collisions with other universes in the multiverse. Every new observation peels back another layer, showing us that this ancient light still has stories left to tell. What's breathtaking is how much we've learned from what seems like simple static. The CMB confirms that ordinary matter, the stuff of stars and planets, makes up less than 5% of the universe. The rest is dark matter and dark energy, mysteries we're still unraveling. And those faint temperature variations, they're the reason we exist. Without them, matter would have spread perfectly evenly, leaving no seeds for galaxies to grow. So the next time you see static, remember, you're glimpsing the universe's baby picture, the moment it took its first breath of light, setting in motion everything that would follow. Imagine the universe as a vast, silent ocean until suddenly, 2 black holes collide, sending ripples racing outward at the speed of light. These aren't waves of water, but something far stranger, gravitational waves, undulations in the very fabric of space-time itself. Albert Einstein first predicted their existence over a century ago, theorizing that cataclysmic cosmic events would warp the geometry of the universe, creating ripples that could travel across billions of light years. But it wasn't until 2015 that scientists finally captured direct proof when LIGO, the Laser Interferometer Gravitational Wave Observatory, detected vibrations from 2 black holes merging over 1.3 billion years ago. That moment didn't just confirm Einstein's genius, it gave humanity an entirely new way to experience the cosmos. What makes gravitational waves so revolutionary is how they carry information no telescope could ever see. Light can be blocked or scattered, but space-time ripples pass through everything, bringing us unfiltered signals from the most violent events in existence. Think of it like listening to a symphony through a wall. You might miss the visuals, but the music tells its own vivid story. Already, detectors have picked up waves from neutron stars spiraling into each other, their collisions forging heavy elements like gold and platinum in a flash of cosmic alchemy. These observations aren't just spectacular, they're reshaping our understanding of how the universe builds itself. Now, researchers are chasing an even more elusive prize: primordial gravitational waves, faint echoes from the universe's first chaotic moments. While the cosmic microwave background shows us the aftermath of the Big Bang, these waves could be a direct recording of inflation, that explosive split second when the universe expanded faster than light itself. Detecting them would be like finding a fossil of the universe's first heartbeat. Next-generation observatories, like the space-based LISA mission or ultra-sensitive ground detectors, might soon tune into these whispers from time's dawn. The implications are staggering. If these primordial waves exist, they could reveal whether our universe collided with others in the multiverse, or if space-time itself has a granular quantum structure. Some theories suggest they might even carry traces of cosmic strings, mythic defects in space-time left over from creation. Every new detection peels back another layer of the cosmic onion, proving that the universe isn't just something we see, it's something we can hear. And as our ears grow sharper, who knows what other secrets the cosmos has been humming all this time? Those tiny quantum fluctuations were the universe's first brushstrokes, invisible ripples that would one day sculpt galaxies. Picture the cosmos in its earliest moments, a seething ocean of energy where particles flickered in and out of existence, governed by quantum uncertainty. At this scale, even empty space wasn't truly empty. It crackled with microscopic variations, regions slightly denser or hotter than their surroundings, like the faintest wrinkles in spacetime's fabric. Normally, these quantum jitters would cancel each other out, vanishing as quickly as they appeared. But then cosmic inflation struck, stretching space itself faster than light could chase it. In that explosive expansion, something extraordinary happened. Those fleeting quantum fluctuations didn't disappear, they got locked in. Imagine blowing up a balloon with tiny dots on its surface. As the balloon inflates, the dots don't just spread apart, their imperfections stretch too, becoming grand patterns. Inflation did precisely this to space-time, magnifying subatomic wrinkles into cosmic mountains and valleys. What began as random variations smaller than a proton grew to span thousands of light years, becoming the scaffolding for everything we know. Here's the beautiful twist: these fluctuations weren't random noise, they followed a precise mathematical rhythm. Scientists analyzing the cosmic microwave background find their fingerprint everywhere. The distribution of hot and cold spots matches predictions of quantum physics with stunning accuracy, as if the universe left us a carefully tuned recipe. Warmer regions where matter was denser became the birthplaces of galaxies. Cooler zones evolved into the vast voids between them. Without these initial imperfections, gravity would have had nothing to grab onto, leaving the universe smooth, dark, and empty. Modern supercomputers now simulate how these seeds grew over billions of years. Starting with those subtle density variations, they show dark matter's invisible tendrils pulling matter into intricate webs, gas condensing into stars, and galaxies spinning into existence, all tracing back to quantum tremors in the universe's first trillionth of a second. Some models even suggest these fluctuations might reveal hidden dimensions or the nature of dark energy. It's humbling to realize that the grandest structures in existence, galaxy clusters spanning millions of light years, owe their existence to whispers from the quantum realm, amplified across eternity. The universe didn't just expand after the Big Bang, it exploded outward faster than the speed of light, stretching space itself in a blink so brief it's almost impossible to comprehend. We're talking about a fraction of a second so small, it makes the snap of your fingers feel like an eternity. This is cosmic inflation, the theory that solves some of the universe's biggest mysteries. Imagine taking a crumpled piece of paper and smoothing it out with a single, swift motion. That's what inflation did to the early cosmos. Before this explosive growth, the universe was a turbulent sea of irregularities, with energy and density fluctuating wildly from one point to the next. But inflation stretched space so rapidly, so thoroughly, that it ironed out those wrinkles, leaving behind the eerily uniform cosmos we observe today. Yet, inflation didn't just smooth things over. It also magnified the tiniest quantum jitters into cosmic landmarks. Think of it like blowing up a microscopic crack in a piece of glass until it becomes a vast canyon. Those minuscule fluctuations, born from quantum uncertainty, were stretched across the universe, becoming the seeds for galaxies, stars, and everything we see. Without them, gravity would have had nothing to grasp, leaving the cosmos a featureless void. It's a delicate balance. Inflation erased the chaos of the Big Bang, but preserved just enough variation to give the universe its structure. What's even more astonishing is how inflation explains two cosmic puzzles at once. First, why does the universe look the same in every direction, no matter where we look? Distant regions of space, too far apart to have ever exchanged light or heat, somehow share identical temperatures and densities. Inflation's answer. They were close together before the universe ballooned in size, pushing them apart in an instant. Second, why is the universe so perfectly flat, with space obeying the rules of Euclidean geometry rather than curving dramatically? Inflation stretched space so much that any initial curvature was smoothed out, like flattening a raisin into a sheet of dough. Scientists didn't just pull this theory out of thin air, it makes precise predictions that match our observations. The cosmic microwave background's temperature variations, the distribution of galaxies, even the way matter clumps together on the largest scales, all of it aligns with inflation's fingerprints. Some models even suggest inflation wasn't a one-time event but part of an endless cycle, with new universes budding off like bubbles in an infinite cosmic foam. Yet mysteries remain. What triggered inflation in the first place? Did it truly end everywhere, or are parts of the universe still stretching eternally? Could there be other universes beyond our own, each with different laws of physics? The search for answers drives experiments like BICEP and the Simons Observatory, which scour the cosmic microwave background for faint imprints of primordial gravitational waves, ripples that could confirm inflation's wildest claims. Every new discovery peels back another layer, revealing just how much the universe's first moments still shape everything we see. Baryon acoustic oscillations might sound complex, but they're essentially the universe's earliest sound waves frozen in time. Picture the cosmos in its infancy, a seething plasma so hot that light couldn't travel freely. Within this dense, glowing soup, particles were constantly jostling, creating regions of higher and lower pressure. These ripples moved outward like sound waves through air, compressing and rareifying the plasma as they went. But when the universe cooled enough for atoms to form, around 380,000 years after the Big Bang, something remarkable happened. Those waves suddenly froze in place, etching their patterns into the distribution of matter like cosmic fossils. What makes these oscillations so valuable is their consistency. Just as the pitch of a musical note depends on the size of the instrument that produced it, the scale of these waves reveals the universe's early conditions. The original sound speed of the plasma determined how far these ripples could travel before freezing about 500,000 light-years. Over billions of years, gravity amplified these subtle density variations, pulling matter into the peaks of those ancient waves. Today, we see their imprint in the way galaxies cluster together, spaced at intervals that mirror those primordial vibrations. It's as if the universe left us a ruler etched into the cosmos, with each mark precisely 500 million light-years apart. Astronomers use this cosmic ruler to measure the expansion of the universe with breathtaking precision. By comparing the apparent size of these oscillations at different distances, and thus different eras, they can track how space has stretched over time. The results are startling. Not only do they confirm the universe is expanding, but they also reveal that this expansion is accelerating, driven by the mysterious force we call dark energy. The spacing of these oscillations even hints at dark matter's invisible influence, showing how its gravitational pull helped shape the large-scale structure of the cosmos. Recent galaxy surveys, like those from the Sloan Digital Sky Survey or the Dark Energy Spectroscopic Instrument, have mapped millions of galaxies to trace these oscillations in unprecedented detail. The data paints a picture of a universe far stranger than we once imagined, where ordinary matter is just a minor player in a drama dominated by dark energy and dark matter. Some researchers are even looking for subtle distortions in these patterns that might reveal new physics evidence of extra dimensions or modifications to Einstein's theory of gravity. What's poetic about Baryon acoustic oscillations is how they connect us to the universe's earliest moments. Those sound waves began as tiny quantum fluctuations, no different from the ones that seeded galaxies. But while inflation stretched them across the cosmos, it was the push and pull of ordinary matter and radiation that gave them their distinctive scale. Today, they serve as both a time capsule and a measuring tape, helping us unravel mysteries that stretch from the Big Bang to the fate of the universe itself. Every galaxy, every void, every filament in the cosmic web carries echoes of that primordial sound, a rhythm set in motion when the universe was just a whisper of what it would become. While light and gravitational waves tell us much about the universe's infancy, there's another, far more elusive messenger drifting through space, one that has traveled nearly undisturbed since the first second of creation. Meet Relic Neutrinos, the ghostly survivors of the Big Bang. Billions of these nearly massless particles pass through your body every second, moving at nearly the speed of light, barely noticing the existence of planets, stars, or even you. Born in the unimaginable heat of the universe's first moments, they've been streaming through the cosmos ever since, carrying stories from a time before atoms or even light could exist in its familiar form. These cosmic ghosts hold clues to an era we can't see any other way. Just 1 second after the Big Bang, the universe was so dense that even neutrinos, which rarely interact with matter, were trapped in the seething plasma. But as space expanded and cooled, these particles broke free, creating a background sea of neutrino radiation that permeates everything. Unlike the cosmic microwave background, which shows us the universe at 380,000 years old, Relic Neutrinos offer a snapshot from when the cosmos was barely a toddler, revealing conditions during nucleosynthesis, when the first hydrogen and helium nuclei formed. Detecting them is one of physics' greatest challenges. Current experiments like Ptolemy and the proposed Tristan project aim to capture these ancient particles by spotting the unimaginably faint recoil when one finally strikes an atom. It's like listening for a single raindrop in a thunderstorm, but if successful, the payoff could rewrite cosmology. Relic neutrinos may hold answers to why matter dominates over antimatter, the true nature of dark matter, or even whether extra dimensions exist. Their subtle gravitational influence might explain why galaxy clusters move slightly faster than predicted, hinting at hidden forces shaping the cosmos. What's breathtaking is how these silent travelers connect us to the universe's most violent beginnings. Each relic neutrino carries energy from an epoch when temperatures exceeded 10 billion degrees, a time when the forces of nature were unified in ways we can barely imagine. They're living fossils unchanged for 13.8 billion years, whispering secrets about how everything began. And as our detectors grow more sensitive, we may soon tune into this primordial neutrino background, adding another layer to the universe's origin story, one written not in light or gravity, but in the faintest tremors of particles that have outlasted time itself. Dark matter is the universe's silent architect, an invisible force that sculpted the cosmos without ever revealing itself. We can't see it, touch it, or detect it with any telescope, yet its gravitational fingerprints are everywhere. Picture a vast cosmic construction site where the blueprints are written in gravity alone. When those primordial sound waves rippled through the early universe, dark matter was there, amplifying their faint vibrations into the grand structures we see today. Without its relentless pull, galaxies might never have formed, leaving the universe a dark, empty expanse. Here's how it worked in the early cosmos: ordinary matter, the stuff of stars and planets, was trapped in a tug of war. Radiation pressure from the searing heat of the Big Bang pushed particles apart, while gravity tried to clump them together. But dark matter, unaffected by light or heat, began collapsing into clumps long before atoms could even exist. These invisible halos became gravitational anchors, pulling ordinary matter into their grasp once the universe cooled enough. The result, that delicate web of galaxy clusters and cosmic voids, each strand tracing back to dark matter's unseen scaffolding. The evidence is written in the sky. When astronomers map thousands of galaxies, they don't spread randomly. They cling to dense filaments, wrapping around enormous voids like foam on ocean waves. Computer simulations show this precise pattern only emerges when dark matter outweighs visible matter by 5 to 1. Even more telling is how galaxies move. Stars at the edges of spiral galaxies rotate far faster than they should if only visible matter were pulling them. Something invisible, something massive, must be holding them in place. But dark matter didn't just shape galaxies, it fine-tuned the universe's very first sounds, those Baryon acoustic oscillations we detect in galaxy surveys. Their spacing and strength depend critically on dark matter's gravitational influence. Think of it like a symphony where the visible universe plays the melody, but dark matter is the resonance chamber, deepening and enriching the notes. Without it, the cosmic web might have been a faint, disordered hum instead of the vibrant structure we inhabit. The hunt to understand this mysterious substance is pushing science to its limits. Underground labs shield detectors from cosmic rays, hoping to catch a rare collision between dark matter particles and ordinary atoms. Particle accelerators recreate conditions of the early universe, searching for hints of hidden forces. And telescopes like Euclid and the Vera Rubin Observatory are mapping billions of galaxies to trace dark matter's shadowy contours in unprecedented detail. What's thrilling is how much we've learned by studying dark matter's absence, the gaps in our observations that point to an invisible hand guiding everything. It's a reminder that the universe operates on scales we're still learning to perceive. And as we peel back these layers, we're not just solving a cosmic mystery, we're uncovering the hidden framework that made our existence possible. Every galaxy, every star, every planet is here because dark matter turned the universe's first whispers into a chorus. Dark energy is the universe's greatest unsolved riddle, an invisible force pushing galaxies apart faster and faster, as if the cosmos itself is trying to escape its own shadow. Unlike gravity, which pulls matter together, dark energy operates in reverse, stretching space-time with a relentless pressure that grows stronger as the universe expands. Its fingerprints are everywhere, in the way distant supernovae appear dimmer than they should, in the subtle warping of ancient light from the cosmic microwave background, even in the stretched-out remnants of those primordial sound waves that once rippled through the early universe. Think of dark energy as a cosmic counterweight to gravity's pull. When the universe was younger and denser, gravity dominated, drawing matter into galaxies and clusters, slowing the expansion forged by the Big Bang. But around 5 billion years ago, something flipped. As space grew emptier and matter spread thinner, dark energy's push overcame gravity's grasp, sending the universe into accelerating expansion. Those Baryon acoustic oscillations, the frozen sound waves imprinted in galaxy distributions, tell this story with startling clarity. By measuring how these patterns appear at different cosmic distances, scientists discovered that the spacing between galaxies isn't just increasing, it's doing so at a rate that's speeding up. What makes dark energy so perplexing is how little we know about it. Einstein's famous cosmological constant, a term he initially added to his equations to keep the universe static, might explain it as an inherent property of empty space itself. But observations suggest dark energy's strength could be changing over time, hinting at something far stranger. Some theories propose it's a dynamic field, like an invisible cousin to the Higgs boson, permeating space with fluctuating energy. Others wonder if it's a sign that Einstein's theory of gravity breaks down on cosmic scales, requiring entirely new physics to unravel. The implications are staggering. If dark energy continues strengthening, it could eventually tear apart galaxy clusters, stars, even atoms in a theoretical Big Rip. Alternatively, it might weaken and reverse, collapsing the universe back into a fiery crunch. Or it could simply fade into silence, leaving the cosmos to expand forever cold, dark, and empty. The echoes of creation we study today, those sound waves, relic neutrinos, and gravitational ripples, are more than just relics. They're clues to dark energy's nature, helping us predict whether the universe's symphony will end with a crescendo, a whisper, or something beyond our current imagination. Next-generation telescopes like the Vera Rubin Observatory and the Nancy Grace Roman Space Telescope are mapping billions of galaxies to trace dark energy's influence with unprecedented precision. By studying how the cosmic web evolves over time, they might reveal whether this mysterious force is constant or evolving, a key to unlocking the universe's ultimate fate. Every measurement, every distant supernova, every subtle twist in ancient light brings us closer to answering one of cosmology's deepest questions. Is dark energy the final note in the universe's song, or merely a prelude to something even more extraordinary? The Planck satellite wasn't just another telescope, it was a time machine designed to capture the universe's first portrait with staggering clarity. Imagine trying to photograph a candle's flicker from miles away, then magnifying that image until every subtle shift in temperature becomes visible. That's what Planck achieved with the cosmic microwave background, measuring temperature variations as tiny as 1 part in a million. Launched in 2009 by the European Space Agency, this mission spent 4.5 years scanning the sky, collecting data so precise it reshaped our understanding of cosmic history. What set Planck apart was its unmatched sensitivity. Earlier satellites like WMAP had mapped the CMB's broad strokes, but Planck's instruments cooled to near absolute zero to minimize interference, detected fluctuations at scales finer than the moon's apparent size in the night sky. These minute details matter because they encode the physics of the universe's infancy. The patterns Planck observed aren't random noise. They're echoes of quantum fluctuations stretched across the cosmos by inflation, frozen into the fabric of spacetime when light first broke free. The revelations were profound. Planck's data pegged the universe's age at 13.8 billion years with an uncertainty of just 1%, a level of precision akin to measuring the distance from New York to Los Angeles within the width of a hair. It confirmed that ordinary matter, the stuff of stars, planets, and us, makes up a mere 4.9% of the cosmos. Dark matter accounts for 26.8%, while dark energy, the mysterious force driving cosmic acceleration, dominates at 68.3%. These numbers might seem abstract, but they're the foundation of modern cosmology, the constants that define everything from galaxy formation to the universe's ultimate fate. But Planck's true legacy lies in how it tested and sometimes challenged our boldest theories. Its measurements of the CMB's polarization hinted at anomalies that standard models struggle to explain. Why does one hemisphere of the sky show slightly stronger temperature variations than the other? Could this asymmetry point to pre-inflationary physics, or even a collision with another universe? Some researchers speculate these quirks might reveal flaws in Einstein's relativity or clues about quantum gravity. Perhaps most tantalizing is what Planck didn't find. Many hoped its data would reveal direct evidence of primordial gravitational waves, the smoking gun for cosmic inflation. While it didn't detect them conclusively, Planck narrowed the possibilities, ruling out entire classes of inflationary models and pushing theorists to refine their ideas. Science often advances by closing doors as much as opening them, and Planck's null results were just as valuable as its discoveries. Today, Planck's dataset remains a goldmine, combed by researchers for subtleties that might unlock new physics. Its map of the CMB isn't just a snapshot of the past, it's a puzzle box, holding secrets about dark matter's nature, the birth of spacetime, and forces we've yet to name. As future telescopes build on its work, Planck's legacy endures, reminding us that every answer in cosmology uncovers deeper questions, and that the universe's first light still has stories left to tell. The next generation of cosmic observatories isn't just upgrading our vision, it's fine-tuning our ability to hear the universe's deepest whispers. Take the James Webb Space Telescope, already revolutionizing infrared astronomy. While Hubble showed us stunning galactic portraits, Webb peers through cosmic dust like a surgeon's scalpel, revealing the formation of the very first stars and galaxies. But its real power lies in spectroscopy, splitting ancient light into precise wavelengths that act as chemical fingerprints. When trained on primordial gas clouds, Webb can detect subtle shifts in spectral lines caused by those primordial sound waves from the Big Bang, letting us hear how matter vibrated when the cosmos was just a few 100 million years old. Meanwhile, gravitational wave astronomy is entering an unprecedented era. LIGO and Virgo opened our ears to black hole collisions, but future detectors like the Einstein Telescope and Cosmic Explorer will be 10 times more sensitive. Buried in their data could be the faintest gravitational wave background, a chorus of ripples from the universe's first seconds. Some theories suggest these waves might carry imprints of cosmic strings, hypothetical defects in spacetime that formed during the universe's violent birth. Others predict they'll reveal quantum gravity effects, showing how spacetime itself behaves at the smallest scales. The most ambitious project on the horizon is LISA, the Laser Interferometer Space Antenna. Scheduled for launch in the 2030s, this trio of spacecraft will form a gravitational wave detector spanning millions of kilometers, sensitive to low-frequency ripples that ground-based machines can't catch. LISA could detect mergers of supermassive black holes from the cosmic dawn, or even the gravitational ringing from inflation's final moments. Imagine hearing the universe's first vibrations directly, like capturing the echo of a shout in a canyon, except the shout was the Big Bang and the canyon is space-time itself. On the ground, projects like the Simons Observatory and CMB-S4 are building ultra-sensitive microwave telescopes to scan the cosmic microwave background with pixel counts in the millions. Their goal, to spot the faint swirls in the CMB's polarization that might be signatures of primordial gravitational waves, the smoking gun for inflation. Some models suggest these patterns could even reveal whether our universe collided with others in the multiverse, leaving telltale bruises in the fabric of reality. What's exhilarating is how these missions complement each other. Webb's infrared eyes, LISA gravitational ears, and next-gen CMB detectors together form a cosmic orchestra, each instrument tuned to a different frequency of the universe's symphony. With every new observation, we're not just adding to our knowledge, we're learning to listen more carefully to a song that's been playing since time began. And who knows, the next big discovery might not come from what we see, but from what we finally hear. What if our universe isn't alone, just one bubble in a frothing cosmic sea? The Multiverse Hypothesis suggests exactly that, proposing a reality where countless universes exist beyond our own, each with its own laws of physics, dimensions, even alternate versions of history. While it sounds like science fiction, this idea emerges naturally from some of our most robust theories, like cosmic inflation and string theory. Inflation doesn't just explain our universe's smoothness, it implies that space-time could be eternally expanding, spawning new universes in an endless cascade. String theory takes it further, suggesting higher dimensional brains might collide like sheets of paper in a cosmic breeze, each impact birthing a new cosmos. The wildest part, we might already have evidence. Subtle anomalies in the cosmic microwave background, like the infamous cold spot spanning billions of light years, could be bruises from collisions with other universes. Picture two soap bubbles gently bumping in some higher dimensional space. The energy from that meeting might leave faint scars in the CMB's temperature patterns. Similarly, primordial gravitational waves could carry echoes of these encounters. If future observatories detect unexpected twists in these space-time ripples, they might reveal not just our universe's birth, but its neighbors too. Critics argue these ideas stretch science beyond testability, but proponents counter with concrete predictions. Certain multiverse models predict specific statistical quirks in the CMB's temperature distribution patterns that telescopes like the Simons Observatory are actively hunting. Others suggest that if our universe collided with another, the event would create a distinct circular polarization pattern in the CMB's light, like a ripple frozen in time. Finding it would be like discovering a cosmic fingerprint on the window between realities. Even if the multiverse remains unproven, its implications are profound. It could explain why our universe seems finely tuned for life. If infinite universes exist, some will inevitably have the right conditions by sheer chance. More radically, it challenges what we consider natural. The laws we take as fundamental might just be local bylaws in one cosmic neighborhood, with entirely different rules governing other realms. The search for these echoes isn't just about mapping the multiverse, it's about probing the limits of science itself. How far back can we trace causality? Can we study realities forever beyond our reach? As experiments grow more sophisticated, we might find that the universe's first sounds weren't just a solo performance, but part of an infinite choir, each voice singing a different tune in the grand symphony of existence. String theory turns the universe into a grand cosmic instrument, one where every particle, every force, even space-time itself emerges from microscopic strings vibrating in hidden dimensions. These aren't the strings of a guitar or violin, but unimaginably tiny filaments of energy, each oscillating at a unique frequency to create the symphony of matter and energy we observe. What if those vibrations aren't just mathematical abstractions, but literal echoes of the universe's first moments? The idea that these strings could harmonize with the primordial sound waves from the Big Bang offers a breathtaking possibility, a single framework that unites quantum mechanics and gravity, bridging the smallest scales with the largest. At its heart, string theory suggests that the fundamental building blocks of nature aren't point-like particles but one-dimensional strings. Their vibrations determine whether they manifest as quarks, electrons, or even the carriers of forces like gravity. The lowest energy vibration might produce a photon, while a higher energy mode could create a graviton, the hypothetical particle mediating gravity. This elegant symmetry hints at a profound connection between the quantum world and the cosmic scale. Those same quantum fluctuations that seeded galaxies might trace back to the collective hum of strings vibrating in the early universe's fiery plasma. The implications ripple across cosmology. If strings exist, their vibrations could have left imprints in the cosmic microwave background or the gravitational wave background, subtle fingerprints waiting to be decoded. Some models even suggest that the universe's expansion during inflation stretched these strings into cosmic strings, filaments of pure energy thinner than an atom but stretching across the cosmos. These relics, if detected, would be smoking guns for string theory, their gravitational waves carrying tunes from the universe's earliest notes. Yet the most radical idea is how string theory reimagines spacetime itself. In this framework, the fabric of reality isn't passive. It's a dynamic network of strings interacting in higher dimensions. The sound of the early universe might not have traveled through space as we know it, but through these hidden geometries, vibrating in ways that shape the cosmos before dimensions as we know them even stabilized. It's as if the universe began as a symphony played in a hall with extra, curled-up dimensions we can't see, their echoes still resonating in the patterns of galaxies today. Challenges remain. String theory predicts a vast landscape of possible universes, each with different physical constants. Finding evidence that pins down our specific version or confirms strings exist at all requires breakthroughs in particle accelerators, gravitational wave astronomy, or even quantum computers. But the payoff would redefine physics. A confirmed link between string vibrations and cosmic echoes wouldn't just explain how the universe began. It would reveal why its music sounds the way it does, from the hum of atoms to the roar of colliding black holes. For now, string theory remains a melody without definitive proof, a hypothesis singing in the gaps of our knowledge. Yet as telescopes peer deeper and detectors grow more sensitive, we might soon catch the harmonics of these cosmic strings, tuning our instruments to frequencies older than time itself. Whether the theory holds or falls, its bold vision reminds us that the universe's first sounds might be more than relics. They could be the key to a grand unification, waiting for us to listen closely enough. Supercomputers have become our time machines to the cosmic dawn, not just modeling the universe as we know it, but rewinding the tape to replay creation itself. These aren't simple animations. They're staggeringly complex virtual laboratories where physicists tweak the laws of physics to see if a universe like ours emerges. Take the Illustris TNG project, for example. Starting with a digital soup of particles representing dark matter and primordial gas, it simulates billions of years of cosmic evolution in weeks, tracking how gravity, radiation, and even supernova explosions sculpt the cosmos. The results are uncanny. Virtual galaxies form with spiral arms and stellar populations that mirror Hubble's deepest observations, all tracing back to those subtle density variations imprinted by the Big Bang sound waves. What makes these simulations revolutionary is how they bridge theory and observation. By adjusting initial conditions, say, the strength of dark matter's pull or the timing of cosmic inflation, scientists create thousands of alternate universes, then compare them to real sky surveys. It's like tuning a musical instrument by ear, searching for the settings where virtual and actual galaxies align. Recent simulations even incorporate quantum fluctuations from the universe's first trillionth of a second, magnified by inflation into cosmic scale ripples. When these match the patterns in the cosmic microwave background, it's a smoking gun that the theories behind them might be correct. One breakthrough came when simulations revealed why galaxies cluster at specific distances, the same 500 million light-year spacing seen in Baryon acoustic oscillations. The virtual universes showed how dark matter's gravity amplified those primordial sound waves, while ordinary matter lagged behind, caught in a tug of war with radiation pressure. Without this intricate dance, galaxies wouldn't arrange themselves in the vast, web-like structures we observe. Simulations also exposed surprises, like how early black holes may have acted as cosmic lighthouses, their radiation clearing fog like hydrogen and accelerating star formation. But the real magic happens when simulations collide with mystery. Some models predict that if dark matter interacts weakly with itself, rather than being completely invisible, it should leave subtle fingerprints in galaxy shapes. Others explore whether alternate forms of inflation would produce gravitational waves detectable by next-generation observatories. Every discrepancy between simulation and observation isn't a failure, it's a clue. When virtual galaxies rotate too fast or cluster oddly, it might hint at unknown particles or modified gravity, steering physicists toward new experiments. The frontier now lies in coupling these cosmic models with extreme quantum physics. Projects like ExaStar are pushing supercomputers to simulate not just galaxies, but the nuclear reactions inside the first stars, those colossal furnaces that forge the universe's first heavy elements. Others are recreating hypothetical cosmic strings, defects in spacetime that could have generated unique gravitational wave patterns. As computing power grows, so does our ability to test wilder ideas. Could colliding universes leave scars in the CMB? Does dark energy's strength change over time? What's breathtaking is how these digital universes have become sandboxes for probing reality's limits. They let us run experiments we could never perform in nature, altering fundamental constants, switching off dark energy, even testing multiverse scenarios. Each simulation is a cosmic what-if, a chance to hear how the universe's first notes might have played differently. And when the virtual and the real align, it's like catching an echo, not just of how everything began, but of all the ways it might have been. Supermassive black holes aren't just cosmic vacuum cleaners, they're the universe's original sound engineers, bending and shaping the primordial symphony in ways we're only beginning to understand. Picture the early universe as a concert hall where sound waves rippled through the hot plasma, and black holes as invisible hands subtly warping the acoustics. Their gravitational might didn't just distort space, it may have left fingerprints on those ancient vibrations that echo through galaxy distributions today. When we map the large-scale structure of the cosmos, we see hints of this interference. The Baryon acoustic oscillations, those frozen sound waves from the Big Bang, should form near-perfect spherical shells around galaxy clusters. But some regions show slight distortions, as if something colossal tugged at the fabric of spacetime while these patterns were still setting. Supermassive black holes, already lurking in protogalaxies when the universe was young, are prime suspects. Their gravity wells could have acted like cosmic funhouse mirrors, stretching and compressing those primordial sound waves as they passed by. Recent simulations reveal how dramatic this effect might have been. When virtual black holes weighing millions of suns interact with sound waves in the early plasma, they create subtle wakes, regions where matter clumps differently than expected. It's like dropping a boulder into a pond and watching how the ripples change direction. These anomalies could explain why some galaxy clusters appear slightly offset from their predicted positions in the cosmic web. The James Webb Space Telescope is now hunting for these discrepancies, comparing ancient galaxy formations against models that account for black hole interference. But here's the twist: black holes might not just distort sound waves, they could amplify them. Some theories suggest their intense gravity focused these vibrations, creating hotspots where galaxies formed more densely. Imagine holding a magnifying glass over a musical score. Certain notes grow louder while others fade. This could explain why we find overdense regions in the universe where galaxies cluster tighter than inflation alone predicts. The smoking gun may lie in gravitational waves. If early black holes warped primordial sound, their mergers should produce ripples in spacetime with distinct harmonics, subtle overtones superimposed on the usual chirp of colliding singularities. Next-generation detectors like LISA could catch these whispers, revealing whether black holes truly tuned the universe's first sounds. Every anomaly we uncover isn't just a curiosity. It's a clue about how the cosmos orchestrated its grand design, with black holes as unlikely conductors in the darkness. Primordial black holes could be the universe's hidden soloists, tiny, ancient, and lurking in the cosmic chorus since the very first notes. Unlike the supermassive black holes we observe today, these hypothetical objects might have formed in the chaotic instance after the Big Bang, when extreme density variations collapsed directly into black holes no larger than an atom but as massive as a mountain. If they exist, they could solve two mysteries at once: the nature of dark matter and the subtle distortions in those primordial sound waves that shaped the cosmos. Picture the early universe as a seething, superheated plasma where quantum fluctuations created pockets of ultra-dense matter. Under the right conditions, these pockets might have collapsed under their own gravity, bypassing the star formation process entirely to become black holes. Some theories suggest they could range in size from a speck of dust to a small moon, scattered across the universe like invisible breadcrumbs from creation. Because they'd emit almost no light, these primordial black holes could be the elusive dark matter we've been searching for, an entire cosmic shadow population hiding in plain sight. Their presence would leave distinct marks on the universe's first sounds. As those primordial sound waves propagated through the early plasma, primordial black holes would have acted like stones in a stream, subtly bending the vibrations around them. Simulations show this could create tiny, localized variations in the cosmic microwave background, slight dips or spikes in temperature that don't fit the standard inflationary model. Some researchers are combing through Planck satellite data for these anomalies, hunting for patterns that might betray the ghosts of ancient black holes. Even more tantalizing is how these objects might interact with gravitational waves. If two primordial black holes collided in the early universe, the resulting ripples in spacetime would carry a unique signature, higher frequency waves than those from stellar black holes, ringing like a cosmic chime. Future observatories like LISA or the Einstein telescope could detect these echoes, offering direct proof of their existence. Others propose that as these black holes evaporated over eons via Hawking radiation, they might have left behind bursts of high-energy particles, faint cosmic fireworks we could still spot today. The implications stretch beyond dark matter. If primordial black holes are real, they'd be time capsules from the universe's most extreme epoch, preserving clues about quantum gravity and the conditions before inflation. Some models even suggest they could have seeded the supermassive black holes we see at galactic centers, growing over billions of years by swallowing gas and stars. Others speculate they might explain bizarre astronomical events, like stars that flare unexpectedly, potential signs of a tiny black hole passing through them. Yet the hunt is fraught with challenges. Primordial black holes could be nearly impossible to distinguish from other dark matter candidates, and their predicted signals are often buried in noise. But with every null result, scientists narrow the possibilities, refining theories about their mass range and abundance. It's a cosmic detective story where the suspects might be everywhere and nowhere at once, invisible relics from the dawn of time, waiting to rewrite our understanding of the universe's first symphony. The Hubble Tension is one of cosmology's most perplexing puzzles, a discrepancy so stubborn it could rewrite our understanding of the universe's expansion. On one side, we have meticulous measurements of the cosmic microwave background, the afterglow of the Big Bang, pointing to an expansion rate of about 67 kilometers per second per megaparsec. On the other, observations of nearby galaxies and supernovas suggest a faster pace, closer to 73. At first glance, the difference seems small, but in the precise world of astrophysics, it's a glaring inconsistency. This isn't just a rounding error, it's a cosmic mismatch that might be whispering secrets about the universe's earliest moments. What makes this tension so fascinating is how deeply it's tied to those primordial echoes we've been exploring. The CMB method relies on the universe's first light, frozen in time, to extrapolate how space has stretched over billions of years. Meanwhile, the local measurements track celestial landmarks like Cepheid variable stars and Type Ia supernova, which act as cosmic lighthouses with known brightness. Both approaches are painstakingly validated, yet they refuse to agree. It's like two clocks, each perfectly crafted, ticking out of sync, and the reason might lie in the universe's opening act. One tantalizing possibility is that unknown physics during the cosmos's infancy altered how expansion unfolded. Could dark energy, the mysterious force accelerating the universe, have behaved differently in the past? Some theories propose it might have surged briefly during the universe's first moments before settling into its current steady push. Others suggest an early interaction between dark matter and dark energy, leaving a fingerprint on how structures formed. There's even speculation about exotic particles that briefly flooded the cosmos, tweaking the expansion rate just enough to leave this lingering discrepancy. Then there's the wild card: what if our measurements aren't wrong but incomplete? The universe isn't a perfectly smooth soup, it's lumpy, with vast voids and dense galaxy clusters. Some researchers argue these irregularities might subtly skew local expansion measurements, creating the illusion of a faster rate. Others wonder if gravity itself behaves differently on cosmic scales, bending the rules we thought were set in stone. Each hypothesis carries implications for how we interpret those primordial sound waves and gravitational echoes. If the Hubble tension stems from new physics, it could mean the universe's first notes were played on an instrument we don't yet understand. The stakes are high. Resolving this tension could unveil hidden layers of cosmic history, from the nature of dark matter to the validity of Einstein's relativity. Upcoming telescopes like the Nancy Grace Roman Space Telescope and the Vera Rubin Observatory aim to settle the debate with unprecedented precision, mapping billions of galaxies to trace expansion in finer detail than ever. Until then, the Hubble tension remains an open question, a reminder that even the universe's oldest echoes might still hold surprises, waiting for us to listen more closely. While cosmic inflation has become the leading explanation for the universe's early expansion, it's far from the only idea on the table. Some scientists argue that inflation solves certain mysteries while creating others, like why the expansion suddenly stopped or what triggered it in the first place. This has led to bold alternatives like the bouncing universe theory, which suggests our cosmos wasn't born from a singular explosion, but emerged from a previous universe's collapse. Picture a cosmic yo-yo, where space contracts to an incredibly dense state before rebounding outward in a new Big Bang. In this scenario, the primordial sound waves we detect might not be echoes of a beginning, but vibrations carried over from a prior cycle, an eternal rhythm of collapse and renewal. Then there's the conformal cyclic cosmology model, proposed by Nobel laureate Roger Penrose, which imagines an endless sequence of universes where the distant future of one becomes the Big Bang of the next. In this mind-bending framework, the cosmic microwave background's temperature variations could bear imprints from black holes that evaporated eons before our universe began. It's as if the universe's first sounds contain whispers from a time before time, encoded in the geometry of spacetime itself. Other theories, like string gas cosmology, propose that the early universe was a tangled web of vibrating strings whose interactions generated the density fluctuations we see today. Unlike inflation's rapid stretching, this model suggests a slower, more chaotic process where the universe's structure emerged from the collective hum of these fundamental threads. The resulting sound waves would have different harmonic signatures patterns that future gravitational wave detectors might distinguish from inflationary predictions. What makes these alternatives so compelling is how they reframe the questions we ask. If the bouncing universe is correct, for instance, the Big Bang wasn't a true beginning but a transitional phase, like the crest of a wave between cosmic epochs. This could explain why the universe appears finely tuned for life, because countless cycles naturally select for conditions that allow complexity to arise. Meanwhile, theories like loop quantum gravity suggest that spacetime itself has a granular structure, which could have altered how sound propagated in the universe's first moments, leaving distinct traces in the distribution of galaxies. Critics point out that many of these models lack inflation's predictive precision, but that's part of the scientific process, exploring blind alleys to sharpen our understanding. The fact that researchers can debate these ideas at all is a testament to how far cosmology has come. A century ago, we didn't even know other galaxies existed. Now, we're comparing intricate theories about reality's first whispers. Each alternative, whether proven or not, pushes us to test inflation's limits and ask whether we're hearing the full symphony or just one movement in a grander composition. The next generation of experiments could tip the scales. Primordial gravitational waves, for example, would be a smoking gun for inflation, but their absence might support cyclic models. Anomalies in the cosmic microwave background's polarization could hint at pre-Big Bang physics, while subtle distortions in galaxy clustering might reveal spacetime's quantum graininess. What's thrilling is that we're no longer just theorizing, we're gathering data that could rewrite cosmic history. Whether inflation holds or falls, these competing ideas remind us that science thrives on dissent, and that the universe's oldest echoes might still surprise us. The universe's first sounds might be more than cosmic accidents. They could be signatures of a reality meticulously calibrated for existence. This is the Anthropic Principle in action, the idea that the fundamental constants and initial conditions of the cosmos appear fine-tuned to allow life to arise. Those primordial sound waves we detect, their precise frequencies and amplitudes weren't arbitrary. If the early universe's density variations had been even slightly stronger, matter would have collapsed into black holes before stars could form. Too weak, and gravity wouldn't have gathered gas into galaxies at all. The echoes we study today exist in a razor-thin sweet spot, a cosmic Goldilocks zone where physics permits complexity to emerge. Take the delicate balance behind Baryon acoustic oscillations. The spacing of those frozen sound waves, about 500 million light-years, reflects the interplay between gravity's pull and radiation's push in the early plasma. Alter that equilibrium by a fraction, and the cosmic web would look radically different. Galaxies might be scattered randomly or clumped into dense knots, leaving no hospitable pockets for solar systems like ours. Even the timing of when these waves froze matters. Had atoms formed earlier, the universe would have remained opaque, trapping light forever. Later, and stars might not have ignited in time to forge the heavy elements essential for life. Critics dismiss this fine-tuning as a tautology. Of course, we observe a universe compatible with life. They argue, because we couldn't exist in one that wasn't. But supporters counter that the odds against such perfect conditions are staggering. The strength of dark energy, for instance, is calibrated to 1 part in 10 to the power of 120. A fraction higher, and space would have expanded too fast for galaxies to coalesce. Lower, and the cosmos would have collapsed back on itself. These aren't minor adjustments, they're cosmic dials set with impossible precision. Where does this leave the echoes of creation? Some theorists propose their evidence of a multiverse, where countless universes with random parameters exist, and we simply inhabit the rare one where physics allows observation. Others see deeper design, a universe engineered with the capacity to comprehend itself. The sound waves themselves don't answer these questions, but they sharpen them. Every measurement of the cosmic microwave background, every gravitational wave detection, becomes a test of whether our universe is inevitable or astonishingly improbable. What's undeniable is how these echoes connect us to the cosmos in a profound way. The same quantum fluctuations that seeded galaxies also made our existence possible. When scientists study those primordial vibrations, they're not just decoding the past, they're uncovering why the universe's music had just the right tempo, volume, and harmony to eventually produce listeners. Whether by chance or necessity, those echoes are more than relics. They're the reason we're here to hear them. Long before telescopes and satellites, humanity sensed that sound held the key to creation. The Hindu Vedas describe the universe emerging from the sacred syllable a vibration that crystallized into matter, echoing through time as the fundamental frequency of existence. In the biblical tradition, God speaks light into being with the command, "Let there be light," as if reality itself responds to divine utterance. Indigenous Australian Dreamtime stories tell of ancestral spirits singing the world into shape, their melodies carving rivers and mountains from formless void. These aren't mere metaphors, they're profound intuitions about how order emerges from chaos, mirroring what modern cosmology now reveals about quantum fluctuations and primordial sound waves. The parallels between ancient wisdom and contemporary science are uncanny. Just as the Big Bang's echoes imprinted structure on the cosmos, the Dogon people of Mali believed creation began with a cosmic word that spun spiraling galaxies into being, a striking anticipation of how sound waves would later seed galactic clusters. Tibetan singing bowls, used for centuries in meditation, produce harmonics that eerily resemble the universe's background hum when translated into audio frequencies. Even Pythagoras' concept of the music of the spheres finds new resonance in the rhythmic patterns of Baryon acoustic oscillations, where galaxies cluster at intervals like notes on a cosmic scale. What's remarkable is how these traditions often describe creation as an act of listening as much as speaking. In Maori mythology, the god Io shaped reality through sacred chants, while Navajo sand paintings depict the universe as a web of vibrational patterns. This mirrors how scientists today listen to the cosmos through radio telescopes and gravitational wave detectors, translating electromagnetic pulses and space-time ripples into audible frequencies. The Chandra X-ray Observatory's sonification of galactic clusters isn't just data analysis, it's a modern echo of the Aboriginal practice of singing up the land, acknowledging that vibration underpins all form. The convergence goes deeper than poetry. Modern physics suggests that at the quantum level, particles may behave differently when observed, as if reality responds to the act of perception itself. This mirrors Hindu and Buddhist philosophies where the universe exists in potential until consciousness interacts with it, much like sound waves needing a medium to propagate. When researchers at MIT modeled the early universe's plasma vibrations, they found the frequencies fell within the range of human hearing, as if the cosmos composed a song waiting to be heard across billions of years. Perhaps these enduring connections explain why NASA sonification projects captivate millions. There's something primal in hearing the Whirlpool galaxy's infrared emissions as a shimmering flute melody, or the Crab Nebula's X-rays as pulsing electronic beats. It taps into an ancient recognition that the universe isn't silent, it's a symphony we're only beginning to decode. From temple bells to quantum fields, the thread remains unbroken, creation sings, and in listening we remember our place in its melody. Every discovery about the universe's origins doesn't just expand our knowledge, it quietly reshapes what it means to be human. When we trace the echoes of creation back to their source, we're not just studying distant physics, we're confronting a mirror held up to our own existence. Consider how radically our perspective shifted when we first saw Earth from space. A fragile blue marble against the void. Now imagine that revelation multiplied by 14 billion years as we comprehend that every atom in our bodies was forged in stellar furnaces and shaped by primordial sound waves. This cosmic ancestry carries an ethical weight. If we're literally made of stardust, does that dissolve human exceptionalism or deepen our responsibility to protect the fragile conditions that allowed our atoms to become conscious? The more we learn about the universe's fine-tuning, the more urgent certain earthly questions become. Those same quantum fluctuations that seeded galaxies also made life possible, an improbable chain of events spanning eons. Yet here we are, burning fossil fuels from those ancient stars at a rate that threatens the delicate balance of our biosphere. There's a profound disconnect between understanding the cosmic miracle of our existence and continuing practices that undermine it. Some philosophers argue that cosmic awareness should inspire planetary stewardship. If the universe went through such extraordinary lengths to produce thinking beings, what does it say when those beings risk unraveling their own habitat? At the same time, cosmic discoveries challenge our definitions of meaning and purpose. Religions and mythologies once anchored human significance in being the center of creation. Now we know we orbit an average star in an unremarkable galaxy, one of trillions. But rather than diminishing us, this revelation could expand our ethical imagination. If life arose here against astronomical odds, might it exist elsewhere? And if so, how does that possibility reshape how we treat other conscious beings, human or otherwise? SETI's search for extraterrestrial intelligence isn't just scientific. It's preparing us for potential moral revolutions. Much like Copernicus' heliocentrism forced a re-evaluation of humanity's cosmic role. The commercialization of space adds another layer. As billionaires fund asteroid mining and Mars colonies, we must ask, who gets to write the ethical framework for exploiting resources beyond Earth? The same inequalities that plague our planet could extend into the cosmos unless we establish equitable principles now. There's poetic irony in realizing that the metals we'll mine from asteroids were themselves forged in the violent deaths of ancient stars. Stellar remains becoming the raw materials for future civilizations. Will we repeat terrestrial patterns of exploitation or honor our cosmic origins with wiser choices? Perhaps most fundamentally, cosmic discoveries remind us that the universe is a story still being told. Those primordial sound waves didn't just create galaxies, they set in motion the possibility of beings who could one day decode them. In that sense, science becomes an ethical act, a way of honoring the extraordinary journey from quantum fluctuations to conscious inquiry. Every time we point a telescope at the cosmic microwave background or listen for gravitational waves, we're not just collecting data, we're fulfilling the universe's capacity to understand itself. And that might be the most humbling responsibility of all, to be the universe's way of bearing witness to its own magnificence. You don't need a PhD to help unravel the universe's oldest secrets, just curiosity and an internet connection. Across the globe, thousands of everyday people are making real contributions to cosmology through citizen science projects, turning home computers into virtual telescopes and smartphones into cosmic microphones. Platforms like Zooniverse host initiatives where volunteers sift through cosmic microwave background data, flagging anomalies that might be missed by algorithms. It's like a digital treasure hunt where the prize could be a clue about dark matter or evidence of primordial gravitational waves. One standout example is the Planck Legacy Archive, where amateurs have helped identify subtle distortions in the CMB's polarization, patterns that professional researchers might overlook amid mountains of data. These collective efforts prove that decoding the universe isn't just for elite institutions. It's a shared human endeavor. What's revolutionary about these projects isn't just their scientific output, it's how they redefine who gets to participate in discovery. Take the Einstein at Home initiative, which harnesses idle computing power from volunteers' devices to analyze gravitational wave signals. While you sleep, your laptop could help spot the faint ripple of a neutron star collision from billions of years ago. Then there's Galaxy Zoo, where over 1 million participants have classified galaxy shapes, revealing how cosmic structures evolve. These collaborations blend human intuition with machine learning, creating a hybrid approach that's uncovered bizarre objects like green pea galaxies and Hani's Vorwerp, a cosmic ghost illuminated by a quasar's long-dead light. The beauty of citizen cosmology lies in its power to transform abstract science into personal connection. When someone marks a faint temperature variation in a CMB map, they're not just completing a task, they're touching the afterglow of creation itself. Teachers use these projects to show students how the universe's blueprint is encoded in data, while retirees find purpose in contributing to humanity's grandest questions. Online forums buzz with enthusiasts debating whether a particular signal is noise or a groundbreaking anomaly, proving that scientific curiosity transcends age, profession, and borders. This democratization has tangible impacts. In 2017, amateur astronomers scanning data from the Kepler telescope helped confirm the discovery of K2-138, a star system with 5 Earth-sized planets, a find that might have taken years without crowd-sourced analysis. Similarly, the Backyard Worlds project has enlisted volunteers to scour infrared surveys for nearby brown dwarfs and rogue planets, objects so faint they evade automated searches. Each discovery chips away at the boundary between professional and amateur, showing that cosmic exploration thrives when it's inclusive. Beyond data crunching, these initiatives cultivate something deeper: cosmic literacy. By engaging directly with real datasets, people gain an intuitive grasp of concepts like redshift, anisotropy, and space-time curvature. they learn that the universe's whispers aren't locked behind equations, they're hidden in patterns anyone can learn to recognize. This shift mirrors astronomy's earliest days, when farmers and sailors used the stars to navigate seasons and oceans. Now, we're navigating the universe's origins together, armed with tools that turn passive wonder into active participation. The ripple effects extend to policymaking and funding. As more people experience the thrill of discovery firsthand, public support grows for missions like the James Webb Space Telescope or LISA. Citizen scientists become ambassadors, explaining to friends why mapping Baryon acoustic oscillations matters, or how primordial neutrinos could rewrite physics. In an era of misinformation, these projects offer a counterbalance, grounding awe in evidence and replacing conspiracy with collaborative truth-seeking. Perhaps the most profound outcome is how they reframe humanity's relationship with the cosmos. When you've personally helped classify galaxies or hunt for CMB anomalies, the night sky stops being a passive spectacle. It becomes a living archive, its secrets slowly yielding to collective curiosity. Every volunteer who joins the search embodies a radical idea that the universe's echoes belong to everyone, and its greatest mysteries might be solved not by lone geniuses, but by countless ordinary people listening together. Many people picture the Big Bang as a massive explosion erupting in some dark, empty void like a cosmic firework bursting outward into nothingness. But that mental image gets it backwards. The Big Bang wasn't an explosion in space, it was the explosive expansion of space itself. Think of it like inflating a balloon covered in dots. The dots don't spread out because they're moving across the balloon's surface. The fabric between them stretches, carrying them apart. In the same way, galaxies aren't flying through space. Space itself is expanding beneath them. A subtle but crucial distinction that changes everything about how we understand those primordial echoes. Another common myth that the Big Bang had a center, some specific point where everything began. In reality, there's no cosmic ground zero to point to. Because space itself was what expanded, the Big Bang happened everywhere at once. Picture baking raisin bread. As the dough rises, every raisin moves away from every other raisin, with no single raisin at the center. That's why astronomers see galaxies receding from us in all directions, no matter where we look. The real surprise, from any galaxy's perspective, it would seem like all the others are moving away because the expansion is woven into the fabric of space-time itself. Then there's the misconception that the Big Bang explains the absolute beginning of everything. While it marks the earliest moment we can currently describe, it doesn't, and can't tell us what came before. The laws of physics as we know them break down at that extreme density and temperature, leaving us with a veil over the universe's true origins. Some theories, like loop quantum gravity, suggest there may have been a bounce from a previous universe. Others propose that time itself emerged with the Big Bang, making before a meaningless concept. What's clear is that the Big Bang wasn't a singular event so much as a threshold, a doorway to the cosmos we recognize. These clarifications matter because they shape how we interpret the universe's first sounds. If we wrongly imagine the Big Bang as an explosion, we'd expect those primordial vibrations to behave like shockwaves from a bomb, traveling outward from a central point. But the reality is far stranger. Those sound waves rippled through the entire universe at once, their frequencies and wavelengths locked in when space was still a seething plasma. Understanding this helps explain why we find the same patterns in every direction. A cosmic fingerprint that's uniform not because everything came from one place, but because everywhere was once compressed into the same infinitesimal point. The most poetic correction, the Big Bang wasn't loud. With no air to carry sound in the early universe, those vibrations were silent oscillations in space-time and energy, more like the hum of a vibrating guitar string than a thunderclap. It's only through the language of mathematics and the tools of modern astronomy that we've learned to hear them at all. So when we talk about the sound of the cosmos, we're not revisiting some ancient noise, we're decoding vibrations that were there all along, waiting for us to develop the ears to listen. The universe's oldest sounds exist at frequencies far beyond human hearing, not just too quiet, but vibrating at pitches our ears could never detect. These cosmic echoes ripple through space at wavelengths measured in light years, oscillating so slowly that a single wave might take years to pass by. Yet through the alchemy of modern technology, we've found ways to translate these whispers of creation into something we can experience. Scientists take data from telescopes and gravitational wave detectors, compressing billions of years of vibrations into seconds and shifting their frequencies into our auditory range. What emerges isn't just scientific data, it's the voice of the cosmos itself, transformed into haunting melodies that resonate deep in our bones. Consider how we perceive sound on Earth. Our ears detect pressure waves vibrating between 20 and 20,000 times per second, a narrow window compared to the universe's full acoustic range. The cosmic microwave background's temperature variations, for example, represent sound waves with wavelengths stretching hundreds of thousands of light years. To make these perceptible, researchers assign higher pitches to denser regions and lower tones to sparser areas, scaling the universe's oscillations into a symphony spanning mere seconds. The result, a chorus of rising and falling notes that mirror how matter clumped together in the infant cosmos, giving us an intuitive grasp of structures that would otherwise exist only as abstract equations. This translation process reveals hidden patterns in the data. When astronomers sonified the vibrations of the Perseus galaxy cluster's supermassive black hole, they discovered rhythmic pressure waves propagating through its hot gas, a deep B-flat note 57 octaves below middle C, vibrating once every 10 million years. Shifted up by quadrillions of times, it becomes a resonant hum that helps researchers identify how black holes heat their surroundings. Similarly, the Planck satellite's cosmic microwave background data transforms into shimmering tones where brighter spots sound higher and more intense, creating an auditory map of the universe's earliest structures. What looks like random static on a graph becomes, when heard, an ordered sequence of harmonies, proof that the cosmos follows musical rules we're only beginning to understand. The emotional impact of these cosmic sounds is undeniable. There's something primal about hearing the universe's vibrations, even in processed form. When LIGO scientists first detected gravitational waves from colliding black holes, they converted the space-time ripples into a distinctive chirp, a rising tone that culminates in a sudden silence as the black holes merge. That sound, spanning just fractions of a second, represents energy equivalent to 3 suns converted into gravitational waves. Played at press conferences, it moved audiences not just as scientific proof, but as visceral evidence of the universe's dynamism. These aren't mere metaphors, they're direct translations of physical reality, bridging the gap between mathematical abstraction and human experience. Yet this sonic translation requires careful stewardship. The choices scientists make, how much to compress time, which frequencies to emphasize, shape our perception of cosmic events. Some sonifications prioritize scientific accuracy, preserving the data's true relationships even if the result sounds dissonant to human ears. Others take artistic license, arranging the sounds into more musical patterns to engage public imagination. Both approaches have value. One reveals the universe as it truly behaves, while the other makes its wonders accessible. Projects like NASA, Universe of Sound, strike this balance beautifully, transforming data from Chandra's X-ray observations into compositions where listeners can distinguish galactic collisions from pulsar pulses by their distinct acoustic signatures. What began as an outreach tool has become a serious research method. Astronomers now use sonification to identify subtle patterns in massive datasets that might elude visual detection. The human ear excels at picking out rhythmic sequences or anomalies in complex audio, skills honed over millennia of evolution. When applied to light curves from distant stars or the timbre of gravitational wave signals, this auditory analysis has uncovered unexpected phenomena, from previously unnoticed starquakes to the faint echoes of black hole echoes. In essence, we've created a new sense organ, a technological ear that listens across both space and time, translating vibrations from the dawn of creation into forms our brains can process. This fusion of science and sensation reshapes our cosmic perspective. Standing beneath a starry sky, we now know it's not silent, it's alive with vibrations we've learned to hear through ingenuity and imagination. From the deep bass of colliding galaxy clusters to the ethereal harmonics of the cosmic microwave background, the universe speaks in frequencies that transcend human biology but not human curiosity. Each translated sound wave carries a dual revelation: how much lies beyond our natural perception, and how brilliantly we've found ways to overcome those limits. The cosmos sings, and though its voice was never silent, we've only just begun to listen. Art and science have always danced together, but never quite like this, where the universe's oldest echoes become symphonies, and raw cosmic data transforms into breathtaking visual art. Take composer John Boswell's Symphony of Science series, where he sonified the cosmic microwave background, turning temperature fluctuations into ethereal piano melodies. The result isn't just educational, it's transcendent, as if the universe itself composed a lullaby from its infancy. Similarly, NASA Chandra X-ray Observatory collaborates with musicians to convert the light curves of pulsars and the radio emissions of distant quasars into pulsating electronic tracks. These aren't arbitrary compositions, they're direct translations of astrophysical phenomena, where a star's flicker becomes a drumbeat and a galaxy's spin morphs into a bass line. Visual artists join this cosmic dialogue too. Data sculptor Rafik Anadol uses machine learning to turn terabytes of telescope observations into swirling, immersive installations. His work Quantum Memories visualizes the quantum fluctuations of the early universe as a dynamic, ever-shifting nebula of light, making the invisible architecture of reality tangible. Meanwhile, the Planck Legacy Archive inspired digital artist Semiconductor to create Brilliant Noise, a film crafted from raw satellite data of the cosmic microwave background. The grainy, monochromatic visuals, often dismissed as noise by researchers, become a hypnotic tapestry, revealing the beauty hidden in scientific rigor. These projects don't just illustrate cosmology, they reimagine it, inviting audiences to feel the universe's scale in ways equations alone never could. What makes these collaborations so powerful is how they bridge the gap between abstraction and emotion. When the LEGO team detected gravitational waves, they released the audio of two black holes colliding, a fleeting chirp that resonated with millions. That sound, though shifted 50 octaves higher for human ears, carried the weight of a cataclysmic event billions of years in the making. Musicians like Valery Vermeulen took it further, weaving gravitational wave data into ambient albums where listeners can hear space-time ripple. It's one thing to read about relativity. It's another to sit in a dark room, eyes closed, as the vibrations of a black hole merger pulse through your speakers. The educational impact is profound. Science communicators like physicist Brian Cox use these artistic interpretations to demystify complex concepts. In his Universal live shows, Cox pairs sonified particle collisions with orchestral arrangements, revealing the musicality hidden in subatomic chaos. Schools now use similar tools to teach astronomy. Students manipulate audio filters to remix cosmic microwave background data, discovering how tweaking frequencies alters the perceived structure of the early universe. These methods don't replace traditional learning, they deepen it, engaging senses that textbooks often ignore. Yet this fusion isn't without controversy. Some purists argue that artistic liberties risk distorting scientific accuracy, that turning supernova remnants into dubstep might prioritize spectacle over substance. But proponents counter that art doesn't dilute science, it amplifies its reach. When painter Lisa Projection visualizes dark matter as a shimmering gold leaf network, or when composer Diego Stocco crafts percussion from solar wind data, they're not simplifying the cosmos. They're expanding its language, offering new entry points for curiosity. After all, Galileo sketched the moon's craters before telescopes could photograph them, and Da Vinci drew fluid dynamics centuries before equations could describe them. Art has always been science's first draft, and its most enduring ambassador. Perhaps the most stirring outcome is how these projects redefine our relationship with the cosmos. Standing before an installation like Raphael Lozano Hemmer's Pulse Spiral, where viewers' heartbeats modulate starlight patterns, the universe stops being a distant abstraction. It becomes a mirror reflecting our place within it. When you hear a sonification of the Andromeda Galaxy's radio waves, a haunting choir of electromagnetic whispers, you're not just observing data. You're eavesdropping on a conversation 13 billion years in the making, one where the boundaries between observer and observed blur into something far more intimate. In the end, these artistic interpretations do more than translate science. They remind us that the universe isn't just a puzzle to solve. It's a story to experience, a song to share, a canvas waiting for every curious mind to leave its mark. Whether through a symphony of primordial plasma or a VR journey through inflationary spacetime, art and science together prove that wonder isn't just the spark of discovery, it's the flame that keeps it burning. What existed before the Big Bang? The question feels almost childlike in its simplicity, yet it unravels the very fabric of how we perceive reality. Modern cosmology paints the Big Bang not as an explosion in space, but as the emergence of space and time themselves, a boundary where our known laws of physics dissolve. Asking what came before might be like asking what's north of the North Pole. Time, as we understand it, may have no meaning in that unfathomable before. Some theories, like loop quantum gravity, suggest a quantum bounce, where our universe sprang from the collapse of a previous one, a cosmic phoenix rising from its own ashes. Others propose a multiverse, where countless universes bubble into existence like water boiling in an infinite pot, each with its own rules and dimensions. Yet even these ideas bump against profound limits. The Planck epoch, the universe's first 10 to the power of minus 43 seconds, is a wall beyond which our equations shatter. At such energies and densities, gravity becomes as volatile as the other forces, and space-time itself may fragment into a froth of quantum fluctuations. It's here that philosophy and physics collide. If time began with the Big Bang, can, before, even be a coherent concept? Saint Augustine wrestled with this in the 4th century, arguing that time was part of creation, a startling prescience to modern relativity, where time bends and warps like fabric. The mystery deepens when we consider entropy. The second law of thermodynamics insists disorder always increases, giving time its arrow. But if the early universe was in a state of near-perfect order, as the cosmic microwave background suggests what set that pristine initial condition, Roger Penrose's conformal cyclic cosmology offers a dizzying answer. Our universe's far future, cold and empty, might become mathematically identical to its ultra-dense beginning, making the Big Bang not a start but a reset in an endless cycle. What's humbling isn't just our lack of answers, it's how the questions redefine curiosity itself. Some echoes of creation may forever elude us, not because our tools are crude, but because the universe's origins might lie outside the framework of cause and effect we're bound to. Like fish trying to imagine life beyond water, we're confined by the very dimensions we seek to explain. Yet the act of asking still matters. Every theory, from bouncing universes to holographic realities, stretches the limits of imagination, proving that the cosmos's greatest gift isn't certainty, it's wonder. If intelligent life exists beyond Earth, how might they perceive the universe's primordial echoes? Our human interpretations, from ancient myths to cutting-edge cosmology, are just one way to decode creation's soundtrack. Consider the possibility of civilizations orbiting distant stars, their senses tuned to frequencies we can't imagine, interpreting cosmic vibrations through frameworks alien to our own. A silicon-based life form might hear gravitational waves as tactile vibrations, while beings evolved in gas giants could sense pressure fluctuations in their atmosphere as a continuous symphony of space-time ripples. These hypothetical perspectives aren't just science fiction, they challenge us to question whether certain truths about the universe's origins might resonate universally, regardless of who's listening. Take the concept of Baryon acoustic oscillations. Humans mapped these frozen sound waves through painstaking analysis of galaxy distributions and CMB data. But a civilization with organically evolved Fourier transform abilities, say, a species whose neural networks naturally pass complex waveforms, might intuit these patterns as instinctively as we recognize a melody. Their creation myths could describe the cosmos as a song interrupted, its verses encoded in the spacing of star clusters. Alternatively, a culture thriving near a supermassive black hole might view space-time vibrations as rhythmic cycles of destruction and rebirth, interpreting gravitational waves from mergers as cosmic drumbeats marking time's passage. The search for extraterrestrial intelligence adds a thrilling dimension to this puzzle. SETI traditional approach scans for radio signals, but what if advanced civilizations communicate through modulated gravitational waves or neutrino pulses? The Laser Interferometer Space Antenna LISA might one day detect not just natural cosmic events, but engineered patterns and alien sonification of their own cosmic history. Imagine receiving a signal that replays their version of the universe's first vibrations, compressed into an audible format as a greeting. Such a message could reveal whether they share our mathematical frameworks for understanding sound waves, or if their physics discovered entirely new harmonic principles. Even more provocative are universals that might transcend biology and culture. All civilizations, no matter their form, would emerge from the same quantum fluctuations imprinted in the early universe. Would they too see these patterns as a tuning of cosmic constants, the Anthropic Principle, the idea that our universe's laws seem finely tuned for life, might find eerie parallels in alien philosophies? Perhaps their scientists also ponder why the primordial sound waves had just the right amplitude to allow structure formation, or whether a multiverse exists where those vibrations played out differently. This thought experiment does more than entertain, it sharpens our science. By imagining how non-human minds might interpret cosmic data, we uncover biases in our own methods. Our reliance on visual representation, for example, leads us to map sound waves as temperature variations in the CMB. A species that perceives the universe primarily through acoustics might have discovered inflationary evidence centuries earlier by focusing on harmonic ratios we overlook. Alternative sensory frameworks could inspire new analysis techniques, like searching CMB data for chiral asymmetries that might indicate handedness in primordial vibrations, a potential universal signature of inflation. The Drake equation famously estimates the number of communicative civilizations, but we might add a new variable: the probability that life forms develop shared cosmological narratives. If multiple species independently link their origins to vibrations in spacetime, it would suggest something profound about the universe's inherent readability. Conversely, radical differences in interpretation could reveal how deeply culture shapes even fundamental physics. Either outcome would revolutionize our understanding of reality's nature and our place within it. While we've yet to find extraterrestrial neighbors, their hypothetical perspectives already serve a purpose. They mirror our assumptions back to us. Every time we sonify black hole mergers or translate quantum fluctuations into musical notes, we're practicing a form of cosmic empathy, attempting to experience the universe through imagined ears beyond our own. This exercise doesn't diminish human achievement. It expands the canvas of discovery. Whether alone or part of a galactic community, our ability to listen to the echoes of creation and wonder how others might hear them is what transforms raw data into a story written across 14 billion years. Detecting the universe's faintest whispers demands technology that borders on science fiction. Imagine building a microphone sensitive enough to pick up vibrations from billions of years ago, except instead of sound waves, you're chasing quantum fluctuations in spacetime itself. Modern observatories like LIGO use laser interferometers with mirrors suspended so delicately that they can detect distortions smaller than 1/10,000th the width of a proton. These mirrors hang from silica fibers thinner than spider silk, isolated from Earth's constant tremors, traffic, earthquakes, even footsteps by layers of active vibration cancellation. It's like trying to measure the width of a hair on the moon while standing in a hurricane. The challenges multiply when hunting for primordial gravitational waves. Unlike the violent ripples from black hole collisions, these echoes from cosmic inflation would stretch wavelengths across light years, requiring detectors of staggering scale. The upcoming LISA mission solves this by placing 3 spacecraft millions of kilometers apart, forming a triangular interferometer in space. Each satellite must track the other's positions with picometer precision, equivalent to spotting a grain of sand on Mars from Earth, while cosmic rays and solar wind buffet their trajectories. To achieve this, they'll use free-floating gold-platinum cubes shielded from all forces except gravity, essentially creating the quietest listening posts in history. Then there's the cosmic microwave background, where subtle temperature variations of millionths of a degree hold clues to the universe's birth. Mapping these requires telescopes cooled to near absolute zero, like the Planck satellite's detectors chilled to 0.1 Kelvin. At these temperatures, electronic noise drops to near silence, allowing sensors to catch photons that have traveled for 13 billion years. But even this isn't enough. To distinguish primordial signals from interference, scientists must account for everything: our galaxy's microwave emissions, dust scattering, even the faint glow of electrons in Earth's upper atmosphere. It's forensic astronomy at its finest, separating cosmic fingerprints from a universe of contamination. Perhaps the most daring frontier lies in quantum-enhanced sensors. Researchers are developing atomic interferometers that exploit quantum entanglement to measure spacetime distortions with unprecedented precision. Picture clouds of ultra-cold atoms acting as exquisitely sensitive rulers, their quantum states shifting in response to passing gravitational waves. Other teams explore superconducting nanowires that can detect single photons from the earliest stars, or pulsar timing arrays that use dead stars as galactic metronomes to catch low-frequency spacetime ripples. Each approach pushes materials science to its limits, demanding superconductors that never falter and atomic clocks that lose less than a second over the age of the universe. What's breathtaking is how these technological feats intertwine disciplines. Cryogenics meets quantum computing, aerospace engineering dances with theoretical physics, all converging to answer questions as old as human curiosity. When the Simons Observatory scans the sky with 50,000 superconducting detectors, or when the Einstein telescope's underground arms listen for spacetime's faintest tremors, they're not just advancing astronomy. They're redefining what's possible, turning the universe's oldest echoes into a language we can finally understand. Every technical hurdle overcome isn't just a victory for science. It's a testament to our species' relentless drive to hear the cosmos sing. The hunt for the universe's earliest whispers is accelerating at a pace that would have stunned astronomers just a generation ago. We're entering an era where cosmic archaeology doesn't just study relics, it resurrects them, using tools so advanced they blur the line between observation and time travel. Picture this: gravitational wave detectors so sensitive they could pick up vibrations from the universe's first trillionth of a second, or telescopes capable of mapping the cosmic microwave background with resolution sharp enough to reveal fingerprints from other dimensions. These aren't speculative dreams, they're projects already underway, like the Cosmic Microwave Background Stage 4 experiment, which will deploy 500,000 detectors across 2 continents to capture the CMB in unprecedented detail. What makes this moment extraordinary is how multiple frontiers are converging. Quantum computing could soon simulate the early universe's conditions atom by atom, revealing how quantum fluctuations birthed galaxies. Meanwhile, neutrino observatories like Ice Cube Upgrade are becoming sophisticated enough to potentially detect relic neutrinos, those ghostly particles from the Big Bang that have traveled undisturbed for nearly 14 billion years. Combined with space-based gravitational wave observatories like LISA, we're building a multidimensional toolkit to explore epochs previously considered unreachable. Imagine triangulating the universe's birth using not just light, but gravity waves, neutrino flows, and quantum signatures. A symphony of cosmic messengers, each carrying different chapters of the same origin story. The most tantalizing possibilities lie in what we can't yet predict. Just as radio astronomy unexpectedly unveiled pulsars and quasars, next-generation instruments may reveal entirely new phenomena. Some theorists speculate we might find evidence of cosmic strings, hypothetical spacetime defects from the universe's birth that would generate unique gravitational wave patterns. Others suggest we could detect imprints from colliding universe bubbles in the multiverse, preserved like fossils in the CMB's polarization patterns. There's even a chance we'll uncover phenomena that rewrite our understanding of physics altogether, perhaps evidence that dark matter interacts with itself, or that dark energy's strength changes over time. What's often overlooked is how these technological leaps democratize discovery. The Vera Rubin Observatory's legacy survey of space and time will image the entire southern sky every 3 nights, generating so much data that citizen scientists worldwide will help analyze it through platforms like Zooniverse. Machine learning algorithms will sift through petabytes of information, spotting subtle correlations human eyes might miss, like whether certain galaxy distributions hint at pre-Big Bang physics. This collaborative approach transforms cosmic archaeology from an elite endeavor into a shared human project, where breakthroughs might come from a student spotting anomalies in an open-access dataset or an amateur astronomer tracking unexpected stellar motions. The philosophical implications run deep. Every layer we peel back doesn't just reveal how the universe began, it reshapes our understanding of what's possible. If we confirm inflation's details, does that suggest our cosmos is one of many? If we detect relic neutrinos, will they show matter and antimatter behave differently in the first second? Each answer promises to be as humbling as it is enlightening, reminding us that the universe's first notes still resonate through every atom, every galaxy, and every curious mind straining to listen. The future of cosmic archaeology isn't just about better tools, it's about developing new ways of hearing, allowing us to eavesdrop on creation itself with ever-growing clarity. The echoes of creation aren't just remnants of a distant past, they're living threads woven into the fabric of our present. Every time scientists decode a new ripple in the cosmic microwave background or capture a gravitational wave from colliding black holes, we're not just collecting data, we're reading pages from the universe's autobiography. These vibrations connect us to moments when time itself was young, offering glimpses of a reality where galaxies were unborn and stars were yet to ignite. It's humbling to realize that the same quantum whispers that shaped galaxy clusters also set the stage for planets, oceans, and eventually, beings capable of wondering how it all began. This pursuit does more than satisfy curiosity, it reshapes our sense of belonging. When we map the Baryon acoustic oscillations imprinted in galaxy surveys, we're not just measuring distances, we're retracing the universe's first footsteps. The iron in our blood, the calcium in our bones, even the silicon in our computers, all were forged in stellar explosions seeded by those primordial density variations. In a very real sense, we are the universe's way of understanding itself, particles from the Big Bang now contemplating their own origins. The line between observer and observed blurs, revealing a cosmos that's not just around us but within us. What makes this journey exhilarating is its unfinished nature. For every mystery solved, like confirming the universe's age with Planck's data, or detecting gravitational waves as Einstein predicted, new enigmas emerge. Dark energy's accelerating push, the Hubble Tension's stubborn discrepancy, the hunt for relic neutrinos, each unanswered question is an invitation to dig deeper. The tools we're building today, from quantum-enhanced sensors to space-based interferometers, will soon peer even further back in time, perhaps uncovering evidence of cosmic inflation or hints of a multiverse. The frontier isn't static, it's expanding as fast as our ingenuity can reach, but the true power of these discoveries lies in their universality. Whether you're a physicist analyzing CMB polarization or a stargazer marveling at the night sky, the cosmos speaks a common language. Citizen scientists classifying galaxies online, artists sonifying black hole collisions, children asking why the sky is dark at night, all are part of this grand dialogue. The universe's echoes don't belong to any one discipline or culture. They're a shared inheritance, reminding us that curiosity transcends borders and generations. As we stand on the threshold of new revelations, one thing is certain: the story isn't over. The next decade could bring breakthroughs we can't yet imagine, detecting actions as dark matter candidates, capturing images of exoplanets with life's chemical signatures, or even hearing gravitational waves from cosmic strings. Each advance will refine our narrative, not just of where we came from, but of what's possible. So whether you're tuning in from a research lab or your backyard, remember, you're part of this unfolding epic. The universe began with a whisper, and its next chapters are waiting to be heard. Keep